and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 4, Lesson 2 on Introduction to Dilations. All right, now back in the last unit, Unit 3, we did a lot of work with various geometric transformations, things like reflections, rotations, translations, and all of those we called rigid motions. And it was because no matter what you did to the object in terms of those three, it still was congruent or identical to the original. It just may have been in a different orientation or a different location or something like that. A dilation, on the other hand, is an entirely new type of transformation that changes the size of an object, all right? So that's what we're going to be getting into today and throughout this entire unit. So let's talk about dilations right from the get-go. Let's learn what a dilation is. So a dilation is a transformation that maps all the points, in a figure in a way that their new distances from some fixed point, which we're going to call the center of dilation, right, are proportional to their old distances, all right? So we got some center of dilation, okay? And let's say some point A, okay? And there's some straight line distance between them, okay? And then we've got that constant of proportionality. You remember that from the last lesson, right? So basically what happens is we just take that old distance, we multiply it by the constant of proportionality. That gives us a new distance, all right? And that's how far we put the image point away from the center, right? And it's in the same direction as our original point. The same direction as our original point. Now, literally what we're doing in this case is we're just taking all these points and we're either stretching them further away from the center or we're shrinking them closer to the center, because the k can do that, and we'll kind of get today into what values of k make the points farther from the center and what values of k make the points closer to the center. The center itself doesn't move, and we'll kind of discuss why that is in one of the exercises. But let's get right into it. Let's take a look at how dilations work in a very, very simple case. All right, exercise number 1. Points A and B have been plotted on the number line below at 4 and 10. Use the origin, the 0 point, as the center of dilation. Letter A asks us to map points A and B after a dilation with a dilation constant of 2. Mark the image points as A prime, B prime. All right, so this is how simple dilations are. Okay, here we've got point A, right, which is 4 units away from the center of dilation. So the center of dilation is the origin, 0. We have a constant of k equals 2, so the image point should now be times 2, should be 8 units away from the origin. So there's our A prime, right? So whereas A was 4 units from the center, A prime now has to be 2 times 4, or 8 units from the center. Same thing with B, right? B is 10 units from the center, times 2 gives us now 20 units from the center. All right, you can really kind of think about this literally as, all right, we have got that distance, 4 times 2 gives us 8 units, and 10 times 2 gives us 20 units. And of course, this is particularly easy because our center of dilation is right there at the point 0, right? So it's very easy. Oh, A is at 4, now it's at 8. B is at 10, now it's at 20. All right? Now, we can certainly have dilation constants that are a little bit uglier, fractional, decimal, whatever. Let's take a look at letter B. Map points A and B after a dilation with a dilation constant of k equals 1/2. Mark the image points as A double prime and B double prime. All right, the same thing, right? So, A was at 4. But if we then multiply that by 1/2, we'll now get a new distance of 2. All right, and again, that's going to be A double prime here. On the other hand, that B, which was at 10, if we multiply it by the dilation constant of 1/2, we now have its location at 5. Maybe I'll make that more obvious. There we go. All right, so it's simple, right? You have to know what the center of dilation is, and you have to know what the constant of dilation is. Once you have those two things, you can simply take the distance that a point is away from that center and then multiply it by the constant of dilation to figure out how far it is from the center at that point. But dilations have kind of a cool property, right? Because it seems like they're all about just like the individual points. But let's take a look at something that's really kind of cool about dilations. Letter C. What was the original distance between points A and B? This is very, very easy. Let's just do this together. When we look at A and B, right, here's A, here's B. A was at 4, B was at 10, so it's just 10 minus 4. The original distance between them was 6 units. All right, that's a piece of cake, right? But now, what are the distances between A prime, B prime, and A double prime, B double prime? Pause the video right now, just look at the number lines, count if you need to, or do that subtraction if you need to, but figure out what the distances are between these two image points and these two image points. Take a moment. Well, let's take a look. So, what do we have? Here's B prime, right, at 20. Here's A prime at 8. So the distance between B prime and A prime is 20 minus 8, which is equal to 12 units. Let's take a look at A double prime, B double prime. Here we've got 2 and 5. So those are 3 units. Now, here's the important observation that's really rather cool. Now remember, when we dilated point A and point B, in both cases, we sort of did them independently of each other. But take a look at letter E. What appears to be true about the distance between 2 points that have been dilated using a certain constant of dilation? So again, the distance between points A and B started at 6 units. After we dilated them both by a constant of 2, now the distance between them is 12 units. On the other hand, when we dilated them with a constant of 1/2, the distance was 3 units. So what do we see from this? Very clearly, the distance between 2 points that are dilated has been scaled by that dilation constant, right? So if we knew that the original distance was 6 units, then after a scaling of a factor of 2, right, now that distance is 12 units because we've multiplied 6 by 2. And if we multiply 6 by 1/2, we get 3. So the important observation is the distance between the 2 points has also been scaled by k. And that's not really necessarily obvious, right? I mean, here we've scaled the distance between a point and the center of dilation, but when we do it twice, strangely enough, then the distance between the 2 points that we both dilated also gets scaled by the same amount. Let's keep working with that, see if it continues to hold. Exercise number 2. Find and plot the images of points A and B after a dilation with a center at C now and a scale factor of 3. All right, now it's always a little bit harder when the point that is the center point isn't the origin, it isn't 0, but it's still pretty easy, right? Now let's do letter A together, right? Here we go. Here we can see that the distance between the point that we're scaling, right, the point that we're dilating, and the center is 3 units. Therefore, if we dilate this with a scale factor of 3, right, then it should be 9 units away and in the same direction, all right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, here's where our A prime should be, okay? Why don't you pause the video right now and figure out where B prime should be? All right, well, it's pretty easy, right? B is 4 units away. If we also stretch that or dilate that by a factor of 3, it should now be 12 units away, which should put it right here, right? That's now 12 units. Now let's see if that observation that we saw in the last problem holds. That's really down here. What does the distance between A prime, or how does the distance between A prime and B prime compare to the distance between A and B? Well, let's see. A is sitting here at 7, B is at 14. So originally, the distance between AB, which we can symbolize just like that, is 7 units. Right? Remember, if we don't have a little segment over the two letters, it literally means the distance from point A to point B. Easy enough. Now, A prime is here at 1, B prime is over here at 22, right? And obviously, 22 minus 1 is 21, which means A prime B prime is equal to 21. And notice the distance is 3 times as large. And that, in fact, is always the case. Whenever we dilate multiple points, then what happens is, even though we dilate each one of them individually, the distance between the 2 points that we dilate gets scaled by exactly the same amount as what we dilated the original points by. So the original points were stretched by a factor of 3 away from the center, and the distance then ended up being stretched by a factor of 3 between the 2 points. That went from 7 units to 21 units. Kind of cool, right? And a little unexpected. Let's keep working with dilations. All right, exercise number 3. Point B below was mapped to B prime using a dilation centered at point A. Letter A asks us, what was the constant of dilation? Show how you found your answer. All right, so this is really, really critical. All right, so let's do this together. So remember, this is my center. Very important. All right, now, the original distance between A and B was equal to 4 units. However, the distance from the center now to the image point, right, that's 3 up to 17, that's 14 units. Okay? So what we know is the following. We know that if we took this and we multiplied it by the scaling constant, we should get this. And that's the whole point, right? Is the scaling constant should take this distance, and when you multiply this distance by that k, you should get this. So we can set up actually a little equation here. We can say 4 times the scaling constant is equal to 14. So the scaling constant must be 14 fourths, which if we reduce would be 7 halves. And if you like it in terms of fractions or decimals, that would be 3.5 or 3.5. Now, I want to point out something, why this is so important. You are very often asked what the constant of dilation is, what the scaling constant is. You can always find that by dividing the new length divided by the old length. Notice, right? 14 was, if you will, the new length, or the new distance, divided by the old distance. Now be careful. A lot of people just think, oh, I'm going to take the bigger one and divide it by the smaller one. Watch out for that. We'll see in the next exercise that doesn't work out so well. All right, what you should always do is think, oh, okay, this was the distance after the dilation. This is the distance before the dilation. So if I take the new distance divided by the old, right, the new divided by the old, that gets me my constant of dilation. Now let's take a look at letter B. This also is important. If point A was dilated using itself as the center and the scaling constant from A, where would its image point lie? Explain. All right, I want you to actually pause the video right now and think about this for a moment. It's important. All right, well, the answer is in exactly the same place. All right? Parentheses, it wouldn't move. Now, unlike the center of dilation, I can move that. I'm going to move that so that we can kind of talk about this a little bit. Why wouldn't it move? Well, again, it all goes back to what a dilation actually does, right? What a dilation does is it takes the distance between the center and the point that you're dilating it, and it multiplies it by some constant, in this case 3.5, to locate its new location. But if you think about the center itself, right, what is the distance between the center and itself, right? Well, that's 0. The distance between A and A is 0. Remember, A is the center here. So if we take that distance of 0 and we multiply by 3.5, then the distance is still 0, right? The center of dilation doesn't move. All other points do. All other points get scaled by this 3.5 or 2 or 1/2 or whatever the scaling constant is. But the center of dilation stays put. And let's write that down. I'd like you to write it down as well. The center of dilation does not move. It just can't. The distance between the center and itself is 0, right? And therefore, when scaled, when multiplied by the scaling constant, the distance is still 0. All right, let's take a look at another problem. Here we go. Exercise number 4. On the number line below, point B is the image of point A after a dilation with a center at point C. Whew. Letter A. What is the scaling constant K of this dilation? Show how you found your answer. All right, so I'd like you to think about this a little bit, and it's a bit tricky, and might I say the answer here is going to be fractional. Get your answer in simplest fraction form. But pause the video now and play around with it a little bit. All right, now we have to be very careful here. Point B is the image, all right? Point A is the original. So take a look at this, right? CA, right, that distance is equal to 6. CB, that distance, is equal to 4. And note that CA, that's the older distance. CB, that's the newer distance, right? B is the image of A after a dilation with a center at C. And therefore, the constant of dilation, which you can still set up this equation for, 6 times K would have to be 4. K would have to be 4 divided by 6, or 2/3. See, in this case, right, we didn't do the bigger number divided by the smaller number, right? It actually ended up being the smaller number divided by the bigger number. And that's because the image point, right, which is B, got closer to the center. It got closer to the center. All right, and again, we'll talk a little bit more about that in a moment, but that is amazingly important. So now let's look at part B. Point E is the image of D after a dilation with a center at C and the same scaling constant as A. Plot point E. All right, well, see if you can figure out on this number line where point E goes. Pause the video now and see what you can do. All right, well, here's the key, right? Let's figure this out first. The distance from C to D, right, is 12 units. Right, we can just do that by doing 22 minus 10. It's going to be 12 units. Let me write that down. CD is 12 units. Now, CE must be our constant of dilation, which is 2/3, times CD. Right, that's just what a dilation is. So 2/3 times 12 would give me 8 units. that tells me that E must lie 8 units away from C in the same direction as D. So that has to lie at 18, right? Because it's got to be 8 units away from 10. So there it is. And notice, by the way, that E also got closer to the center of dilation. If one point gets closer to the center, all the points get closer to the center. Also, if one point gets farther away from the center, all points get farther away from the center. So let's now kind of make a very, very important observation about scaling constants and dilations. An amazingly important observation, right? Exercise number 5. Complete the following with what must be true about the scaling constant K. Letter A. If the image point lies farther from the center than the original point, then the scaling constant must be blank. And letter B, if the image point lies closer to the center than the original point, then the scaling constant must be blank. Well, pause the video now and see if you can think about how these two sentences must get finished. All right, well, we've seen a few circumstances where image points got closer, and we've seen some where they get farther. And it basically boils down to this. If an image point gets farther from the center, then the scaling constant must be greater than 1. All right? And if the image point lies closer to the center, then the scaling constant must be less than 1. Now be careful. You don't want to say something like non-fraction and fraction. You don't want to go there, because you can certainly have fractions greater than 1, right? 3 halves, we had 3.5, right? 7 halves in one of our problems. But the plain fact is, if you have a scaling constant like 3, then everything is going to be triple the distance away from the center that it began. On the other hand, if you have a scaling constant like 1/2 or 1/4 or 1/3 or 1/10 or something like that, then all your points are going to be much, much closer to the center than where they began. All right? Scaling constants greater than 1 means that things are getting bigger. Scaling constants less than 1 means things are getting smaller. And it's that simple. All right, let's summarize. So for the first time in this lesson, we saw a transformation, a geometric transformation that wasn't a rigid motion, right? Most certainly, since rigid motions don't change distances, and that's pretty much what dilations are all about, a dilation isn't a rigid motion. The only way a dilation would be a rigid motion is if the scaling constant was equal to 1. But quite frankly, if the scaling constant was equal to 1, then it's really not a dilation. Nothing's happening at all. We also saw, right, the fundamental idea of a dilation. This idea of like moving points away from or towards the center of dilation by some kind of multiplicative, multiplying constant. If those constants are bigger than 1, then all the points become distances that are farther from the center. And if that scaling constant is less than 1, then all the points are getting closer to the center. We're going to work with those a lot more in the next lesson. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.